one of the best reasons not to worry too much about catastrophic climate change is ironically that the natural greenhouse effect is already so monstrous that by itself it would cook the Earth. And I mean global boiling, fair income.
Humanity is in the hot seat. The era of global warming has ended. The era of global boiling has arrived. The air is unbreathable. The heat is unbearable.
It's a bit like, oops, I left the climate on the stove and it boiled over. Let me check outside. Nope, not boiling. And I seem to be able to breathe, but Guterres is right in one way. If it was just up to the sun and the natural greenhouse effect, the climate would be at least another 20 degrees hotter than it actually is. And that's close enough to boiling for me up here in North Queensland, where it's already pretty hot. Now, I'm going to talk about the natural greenhouse effect caused by natural carbon dioxide and water vapour. And water vapour is by far the biggest greenhouse effect, most important one, greenhouse gas. This natural greenhouse effect, many people don't even know about, or they greatly underestimate it. But because it is so monstrous, it means there must be something else that is equally monstrous that counteracts it to make the Earth livable, more like tepid than boiling. And that greenhouse crusher will mean that the human greenhouse effect caused by all that extra wicked carbon dioxide, well, that will also be counteracted to a similar degree. Now, you might be wondering what that could be, and there are a few things, but I'm going to focus on something very tropical because that's where I am. These things, well, they're big and they're bad, and there's about 1,000 of these greenhouse crushers out there in the wild, in the world, somewhere. But first, let's look at a little bit of greenhouse theory, and along the way we will see some surprising things about how the greenhouse effect works. I used to teach meteorology and geophysics PhD students at James Cook University, and one of the subjects was radiative transfer, how solar radiation heats the surface and how the greenhouse gases such as carbon dioxide, natural carbon dioxide, and water vapour slow down, in the inverted commas, that energy going back to space. And I remember as clear as a day seeing a diagram similar to this one when I was learning this stuff myself, and it showed that if the greenhouse effect had its wicked way and there were no other processes, the surface, as we mentioned before, would be a good 20 degrees hotter. You can argue about the exact number, but it is a huge increase. Now, this graph was taken from a paper a fair while ago by Syakura Manabe, who won this recent Nobel Prize for his work on climate. So this is not some climate skeptic lunatic's result, though I should say Manabe does worry about catastrophic climate change. Anyway, this graph shows the temperature of the air on the x-axis versus the altitude up to the top of the troposphere, which is 10 to 15 kilometres thick. This is the most important layer of the atmosphere. So up high, of course, the air is very cool, and for every kilometre you come down in altitude, the air increases by 6.5 degrees until you get to the surface where it's about 15 degrees Celsius or maybe 290 Kelvin. But if it was just the greenhouse gas by itself, the temperature could easily be 330 Kelvin, and the temperature changes in the vertical would be double or more of what we actually find in the atmosphere. Now, of all the physics of the atmosphere, most of it is horribly complicated to model. The flow is chaotic. Things like clouds we don't even understand the basic physics for. I mean, look at the complexity of this picture. I've done a lot of mathematical modelling and computer modelling, and there's nothing more complicated and chaotic and non-linear than this. Modelling these storms, yes, you can predict roughly where they're likely to occur, but beyond that, very difficult. But as we shall see, these storms are crucial to understanding climate. And ironically, the physics of what we call the radiative transfer of the infrared radiation, the greenhouse effect, is relatively easy to model, with the first work being done way back in 1913. And there's a very nice recent paper that's done this work very accurately using the knowledge of the spectral responses, the spectral lines of the greenhouse gases. So this huge temperature at the surface, if we just have the greenhouse effect, is relatively uncontroversial. But what it means is profound, because it means that the climate systems, all the dynamics, works to massively reduce this horribly huge greenhouse effect, because we don't get this very high temperature at the surface. And what is this monstrous cooling effect? Well, it's complicated, but it has a name. You may have even heard about it. It's called the weather. All those data at day, hour by hour movements of air, the clouds, actually even the ocean currents, and especially the massive thunderstorms in the tropics, the fronts that raise air into the upper atmosphere, all those dynamics, all those thermodynamics, all that hot air rising, when all added up, greatly reduce the temperature increase from the greenhouse effect. In other words, there are very powerful negative feedback mechanisms acting on the climate. So any change, human or otherwise, should not grow and reach some tipping point and end up in the end of the world. Let's go into a little bit of the physics of this. So looking at this diagram of the Earth and the atmosphere, the sun heats up the Earth and atmosphere radiates back into space infrared radiation, basically long wavelength light. All objects radiate infrared. You're radiating infrared now. But especially greenhouse gases in the air radiate infrared. And the hotter they are, the more they radiate. In fact, if your eyes could see all the wavelengths of infrared, then the air itself would, right around you, would appear to glow. If only our eyes could do that, it would be so cool. Everybody would be able to understand the greenhouse effect so much better. Now, when the amount of sun's energy coming into Earth equals the amount radiated by infrared radiation, then there's an energy balance and the Earth remains at the same temperature. And by the way, it's the greenhouse molecules like carbon dioxide and water vapor at the top of the atmosphere that radiate a lot of this energy. So yep, greenhouse gases, they can cool things too. That often surprises people. Now, the level at which the greenhouse gases cool to space, well, that depends on the wavelength. But ballpark height is very ballpark, 5 to 10 kilometres, basically high up the top half of the troposphere. But the sunlight, except for that's reflected by clouds or the Earth's surface, it goes straight through the atmosphere. So the atmosphere is effectively heated from the bottom. And the surface radiates infrared upwards, and some of that just barrels straight through the atmosphere into outer space, and that's the end of it. But much of the energy is absorbed by the greenhouse gases, so the air at the bottom gets hotter. And this is where the greenhouse gases make things hotter. So for energy to make its way from the bottom of the atmosphere, where it's hot, to the level at the top where it can radiate back to space, and to do that by radiation from the greenhouse gases, you need to have a very large temperature difference between the bottom of the atmosphere and the top of the atmosphere. That's the greenhouse effect. This is a model of the atmosphere. Top of the atmosphere, bottom of the atmosphere. The sun might be up there, but it's effectively heated from the bottom. Now, I'm sure many of you will have guessed what the mechanism that will not allow this huge greenhouse effect to go unchecked, because air does not just sit stationary. When you cook it, you can get it really hot. There will be vertical movements of air in huge convection cells, especially around the tropics. So these are the great thunderstorms. There are about 1,000 of them at any given time on Earth. They are the pistons of the great heat engine that drive ultimately most of the Earth's circulation. And they move directly energy from the surface to the top of the atmosphere, where that energy can be radiated to space. The thunderstorms is essentially a huge pipe driving energy from the surface to the top of the atmosphere. So it is the massive churn of the weather that takes the natural greenhouse effect from being a potential disaster to make our life livable. Takes the greenhouse effect from being a deadly tiger to a nice little pussycat. Look at this example from northern Australia. Those storms are like the boils of a vigorously boiling pot, convecting energy, in this case, to the top of the atmosphere. When the ocean gets hot, those storms are inevitable, and the hotter the ocean is, then the storms will become even bigger, even more frequent, or both, and transport more energy to the top of the atmosphere. And these storms are violent, and the energy is utterly colossal. Big storms completely dwarf things like nuclear explosion. Watch this storm work its way across the Gulf of Carpentaria, and a line of clouds coming from the top and streaming away to the southeast. In fact, I recorded this satellite image because I could see the cirrus clouds above me here, many hundreds of kilometres away from where the storm actually was. But it's not just the clouds that are radiating energy back to space, it's actually the clear air itself emitting, glowing up there at the top of the atmosphere as it moves generally towards the poles. It keeps emitting energy to space. And ironically, when it sinks, often in areas which are very hot, like Central Australia, the Sahara Desert, that is where the cooling of the Earth is very effective, but that's another story. So the storms are part of the Earth cooling system to prevent the greenhouse effect cooking us. They are not the only coolers, but they are certainly crucial. They help stabilise the Earth's atmosphere. So while you're contemplating that happy eventuality, perhaps like and subscribe, and if not, well, I apologise for wasting your time. And yes, humans are putting a bit more greenhouse gas into the atmosphere, but compared to all the water vapour that's already there, it's actually not a huge deal and should only add to a degree or two of temperature change, largely because of these natural negative feedbacks. But you should not be surprised that the Earth's atmosphere is clearly self-stabilising. Although the climate has fluctuated dramatically over hundreds of millions of years, it stays within bands of very livability, mostly far hotter than today. At least the temperate regions have been far hotter. The tropics tends to stay pretty similar to what it is today because of all these storms. And in these hundreds of millions of years, the Earth has suffered huge shocks, carbon dioxide levels 10 times what we have today. We've had things like asteroid impacts, which have put up so much material into the atmosphere. It's wiped out most of life on Earth and changed the climate dramatically. But the climate comes back to livability. Volcanic eruptions have done the same thing. The climate hasn't boiled away, and those were far higher, bigger effects than a little bit more carbon dioxide. And of course, this raises the question of what caused the warming of the climate in the last couple of hundred years, and even more fundamental questions about what's caused the other far more massive climate fluctuations of the past. Even the changes in the climate of the last few thousand years, when the climate was often much warmer than it is today. The answer is we just don't know, but the climate change is a fact of life on Earth. We can be thankful that the Earth's natural systems tend to stabilise the climate, but we've also got to get used to the fact that climate change, it changes just in the same way as the weather changes. And if you really need to worry about the end of the world, and it seems to be a common theme over the ages, everybody over the ages has seemed to be worried about something ending the world. Well, worry about maybe climate change from huge volcanic eruptions. They occur far more regularly than you think. Or maybe worry about nuclear war. It only needs some crazy guy to lob a nuclear firecracker in the wrong direction. And really, we won't be worrying about climate change of a couple of degrees, especially if you live in Canada or Scotland where 2 degrees warmer, I really can't see as a big deal. But I think I'm going to worry about artificial intelligence. I'm sure that robot vacuum cleaner looks at me funny at times. They're probably going to murder us in our beds in our sleep one day. But for now, I'm going to go outside, I'm going to smell the roses, and I'm going to watch some thunderstorms cool the planet.